I want to talk today about trends in something called lattice energy. And before we do that, we need to talk a little bit about what we mean by lattice energy. And in order to start that conversation, I want to look at sodium chloride and the energy changes that happen in making sodium chloride from its two elements, sodium and chlorine. And at first glance, you might say, well, it's an ionic compound between sodium ion and chloride ion, so it would be the sum of the energy of forming two positively charged sodium atoms from sodium metal and forming two negatively charged chloride ions from chlorine gas. The two electrons that the sodium gives off are picked up by the chlorine gas, and the sum of those would give you the energy of formation for the enthalpy of formation for sodium chloride. Well, it turns out that it's a lot more complicated than that. There are a couple of things that I don't want to focus on today, like the phases of matter involved going from solid sodium ions to gaseous sodium, or solid sodium metal to gaseous sodium metal, and so on. But what I do want to focus on is the fact that once you form these positively charged ions and these negatively charged ions, they're going to attract each other. Attraction between a positive and a negative ion is a very favorable thing. They're going to pull each other together to form some sort of three-dimensional lattice with positive and negative ions attracting one another. And the energy given off when these positive and negative ions come together is called the lattice energy. The lattice energy can be calculated from the product of the charge on one ion times the charge on the other ion divided by the radius, the distance between the nuclei of the two ions, times some constant, which we're not going to worry about. What I do want you to notice, though, is that the charge terms are on the top, so as the charges get larger, you might expect the lattice energy to go up. And the radius is on the bottom, so as the ions come closer together, the lattice energy goes up. And that makes sense. Bigger charge, more electrostatic attraction. The closer they get, or the smaller the radius, the more attraction. If we look at a series of compounds, I just want to look at this series to start with. The chlorides, lithium, sodium, potassium, and cesium, we can actually look at a chart of data for these ions. I'll leave it right here. And you can see that as we go down the periodic table, the lattice energy gets less. And this is because as we go down the periodic table, the cation gets bigger. The two ions are further apart. Another way of saying that is the radius is larger. So the EL, the lattice energy, gets smaller. So as we go down the periodic table, as the ions get bigger, the lattice energy gets smaller. If we look at the effect of charge, in this case we're going to compare sodium fluoride versus calcium oxide, you might expect from the radius, the R term, that sodium fluoride would be larger in terms of lattice energy because the two ions are closer together. But you'll notice that calcium oxide, even though it has a slightly larger radius, has a +2 charge on or a 2 charge, a +2 and a -2 on each of the ions. That means that this Q term is going to be a lot larger than it was for sodium fluoride. 2 times 2 is 4 versus 1 times 1 is 1. So you might expect it to be somewhere on the order of 4 times larger. And if we look, it's -910 versus -3414. So it does match our prediction that the larger charge on the calcium oxide gives a larger lattice energy. We can summarize these things by saying lattice energies are more exothermic as the radius of our ions decrease, and lattice energies are more exothermic as the charge on our ions increases.